Section 1.4 Matrix equation AX equals B. A fundamental idea in linear algebra is to view a linear combination of vectors as a product of a matrix and a vector. Let's see this definition. A is an m by n matrix. A1 to an are is columns, and X is in Rn. Then the product of A and X, denoted by AX, is the linear combination of columns of A using the corresponding entries of X as weights. Let's see this equation. AX, matrix, a vector multiplication product, can be written along with detailed columns and here entries of X. So we can write this one as a linear combination. Matrix equation is of the form AX equal B, where B is a column vector of size m times 1. Okay, let's see this example. This is a matrix equation, and matrix A and X and right hand side a B. And this matrix equation can be written in this form: x1 times the first column A1 plus x2 times the second column A2 equal right hand side. Once it is written in this form, it is a vector equation. Now here, and if we write it in detail row by row, then we can reshare this system. And x1 plus 2x2 equal 1, that's the first equation. 3x1 plus 4x2 equal minus 1. That is the second equation. So that is a linear system. So all are equivalent. It can be written in this linear system, and or in vector equation, or in matrix equation. Here we have a theorem. A is an m by n matrix having A1 to An, here the columns, and X is in Rn and B is in Rm. Then the matrix equation has the same solution set as the vector equation, because this one and that one are the same, which in turn has the same solution set as the system with the augmented matrix. When we try to solve this vector equation, we may start with here the augmented matrix, or from here we start with this matrix, and so that eventually and the solutions from each one must be the same. We have another theorem: existence of solutions. A is an m by n matrix, then following statements are logically equivalent: all true or all false. That means one of them is true, then the others must be true. If one of them is false, then the others must be false too. Okay, let's see here. For each B in Rm, for every choice of B in Rm, the equation has a solution. So this is a condition for A. The given matrix and Ax equals B has a solution for every choice of B. And that statement, and here the second statement, each B in Rm is a linear combination of columns of A. So here, if it has a solution then it can be written, the right side can be written as a linear combination of columns of A. We can easily accept this equivalence. And also here, the columns of A spans Rm, because a linear combination of columns of A makes every B in Rm. That means that the columns of A span Rm. Right? Okay, here. And final one is A has a pivot position in every row. If A has a pivot position in every row, then for any choice of right-hand side, B, here the augmented matrix has can be solved, right? Only in consistent cases that in a row, at least one row, here everything over there is 0 and non-zero. But it cannot happen because this matrix itself has pivot position in every row, so that we don't have the case that 0 over there and non-zero. So that if A has a pivot position in every row, then AX equals B is consistent, right? So eventually these four statements are equal logically. Okay, here we have three vectors, and question is, does these vectors span R3? Why or why not? Okay, so that's the question. So that here, to show this one, we may check one of them true, one of A, B, D is true, then C must be true. So that one is for each choice of B, and every choice of B we have to do it. So it is a little bit cumbersome. So that let's try to use this one. So once we check this one, then that must be, if this is true, then that must be also true, right? Okay, the question is related with that C statement. Now we are checking D statement because it's a simple. Okay, so we consider a matrix here, and so that we include here three vectors v1, v2, v3, and so that is a 0, 0, 3, and 0, minus 3, and 9, and 4, minus 2, and minus 6. So the span R3 is the same as, now columns of this matrix span R3, right? The R3 is the same as has a pivot position in every row. Okay, so check that D statement. Okay, from here, now this is now non-zero column, this is non-zero entry, so we can interchange, and this third row and first row, for example, then it's a 3, 9, minus 6, and second row is the same, 0, minus 3, and minus 2, and 0, 0, 4. Okay, for that one, you can easily see this is a pivot, that is pivot, that is pivot. So the matrix has a pivot position in every row, right? Quite easily we can check it, so that is true, so that must be true. So for the question, it is yes, along with that reason. Okay. Now, thus the vectors, 3 vectors span R4. Okay, let's try to use the same technique again. So we try to make a matrix A collecting these three vectors, so that 1, 0, 1, minus 2, and second column 3, 1, 2, minus 8, and then minus 2, 1, minus 3, and 2. Okay. For this question, we can answer easily even without doing any further computation. The reason is, now if we try to check statement 4, then here this must be false for given this metric, because it requires a pivot position in every row, but there are only 3 columns, so maximum number of pivots must be 3. However, we have 4 rows, so that at least one row cannot have a pivot position, so that the answer for this question is no. Quite easy, you can see that. Now let's do some further computation, and so that we will check the answer. Okay, now this is a pivot, so 1, 3, minus 2, and we'll try to eliminate below 0, 1, 1, and subtraction will make here 0, subtraction will make minus 1, subtraction will make here. Okay, so that just a moment, that is subtraction, there's a minus 1, subtraction, so that will make 1 here, right? And then for this one, now twice addition, that will be 0, twice addition minus 2, twice addition, so that is a minus 2, right? Okay, from this one, 1, 3, minus 2, okay, the first row. Now there's pivot, and we have to eliminate below of the pivot, so 0, 1, 1, and then adding this row to the third row, we have that is 0, and addition must be 2, and now we are adding twice added, then that must be now 0 row. Okay, so here we have pivot, 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 so 3 pivots, but there are 4 rows, so that this last row cannot have a pivot position. So the statement D is not true, which means here statement C also must be false. Okay, so the answer for the question is no. Okay, now we have true or false question. The equation AX equal B is referred to as a vector equation. Is it true? There's no vector involved, and here this is metric, so that it is referred to as a metric equation, so it is false. Part B, each entry in AX is the result of a dot product. This is true, and we didn't consider the concept of dot product so far. However, and that is true, dot product means that if we have, for example, u vector, that is u vector, that is now u1 and u2, u3, and now v vector, 3 component again of v1, v2, and v3, then from here u dot v is defined to be, okay, component wisely we multiply the quantities and then add them, so that is u1 v1 plus u2 v2 plus u3 V3. So that is the definition of dot product. In matrix vector multiplication, once a matrix is given and here a vector is given, then the result entry here is basically first row and the column dot product will occupy this position. Second row and vector will occupy this position, and so on, so that each entry in matrix vector multiplication is the result of a dot product. So it is true. We'll study dot product later in detail. If A is in R m by n, and if ax equal b is inconsistent for some b, that means that for some choice of b, the linear system has no solution, then A cannot have a pivot position in every row. Is it true? Yeah, it must be true. If A has a pivot position in every row, then here for every choice of B, it must be consistent. That is coming from this theorem. If A has a pivot position in every row, then now for every choice of B, this system has a solution, so it is consistent, right? Okay. So C must be true. If the augmented matrix has a pivot position in every row, then the equation AX equals B is inconsistent. Is it true? Okay. For some cases it's true, but not always. Okay. For example, now in augmented matrix, here it has a pivot position every row, but a pivot position is appearing in the, except the last column, pivot position appears over there. Then it is consistent. It has a solution. But once pivot position is appearing, for example, here the last pivot position is here, then in this case 0 is non-zero, so that it is inconsistent. So only some part of the cases is true, so that the statement is not true, is false. Okay? Okay, this is the end of the section. Thank you.